Okay, here we're going to talk about slant or oblique asymptotes, and then also holes. So you have a slant or oblique asymptote, this SAROA, if the degree on top is exactly one more than the degree on bottom, is exactly one more than the degree on bottom. And so we can find these slant asymptotes algebraically by, once again, factoring and canceling. So we do a lot of factoring and canceling, and then actually dividing P of x divided by Q of x. So we're going to use synthetic division. I mean, you can also do this in your calculator as well. And just look at the graph and maybe find the equation of that line that you see on the graph. But we're going to go ahead and do this with this example. So we're going to find the synthetic or slant asymptote for this function. Notice that nothing needs to be factored. And then remember, with synthetic division, placeholders are important. So this can be written as x squared plus 0x plus 0 to get all your placeholders. So go ahead and pause the video and try to divide that synthetically, and then we'll go through that together. With our synthetic division, the 0 goes in the box. We're divided by x minus 9. So x equals 9 is the 0. So we put 9 out here. Then we have 1x. We have 1x squared, 0x, and then 0 is my constant. And I bring that 1 down. I get 9 times 1 is 9, and 0 plus 9 is 9. And then we have 81. And so this function can be written as x plus 9 and then plus, oops, that's 8. Oh, that's just, what did I do? Here we go, 81. I wrote my 8 and my 1 in weird spots. So this function here, when you actually divide it, could be written as this. Should I get my signs right? And so this is kind of a neat thing to do, and I would encourage you to do this. Graph this in a Desmos or a graphing calculator, and graph this, but then also graph this slant asymptote. So notice this is a line with the y-intercept of 9 and a slope of 1. So this function is almost the line. So I'll go ahead and actually write this down in case we want to say how we write our slant asymptote. It's almost a line, but then it has this other stuff, which when you look at the graph, you'll see kind of a vertical asymptote and kind of a blip in the graph type thing. Other than that, it looks just about like this line, because the graph will approach this line but never cross it. So that's a slant asymptote. And the holes is the other one, which we mentioned in the other video, if you watch that. Holes is when a factor appears on top and bottom of the fraction. So to find the hole, you look and say, okay, well, this factor cancels, so that's gone. It's not a vertical asymptote, but there is a hole at x is equal to 2. And if you want to find the actual location, the y value, then just plug 2 back into the original equation. Well, not the original one, sorry, at the reduced equation after you cancel. Because what it really is, it's kind of a limit, but we'll do this kind of quick version of it, is if you plug 2 in here, it's going to give you 0 over 0. And it's really undefined. But if I plug 2 in just to x squared, if I say f of x is equal to x squared, then it's going to look like you get, I should have written that differently, I'm sorry, but we'll just say that's 4. So this point, hole at x equals 2, or you could say a hole at 2, 4. So your graph, because these reduce or cancel, on the graph it's going to look like business as usual for x squared, except really when we get to 2, we have this place where it's undefined. And so at that single point, there's a hole, and literally like in the graph, like it would look like, say this is my graph, it looks just like a hole, right? We just use a hole there. That will not show up on most graphing calculators. So you have to be aware that it is there. But when you graph, you just put a little hole where it is. Okay, and then in the next video, we will put this all together and we'll actually graph some rational functions by hand.